Thank you, Bruce. I was genuinely nervous about what kind of introduction I was going to get, but that was probably the nicest one of the day. Yeah, thank you for having me here in Bucharest. My first time. I'm having a great time. Everyone I've met was very lovely, and I've really been enjoying the talks that have been going on today as well. Did the audio just kick in? Okay, I can suddenly hear myself better. Okay, so today I'm here to talk about things going wrong, I guess, because on the web, sometimes, shock and horror, things go wrong. And these are some of the things you might see when something's gone wrong. They may look very familiar. Some of you are going, did I just see a polar bear on skateboard? Yes. And as an industry, of course, we spend a lot of time and effort trying to make sure that these kind of things don't happen. And that's not easy. And it's not cheap either. Companies spend hundreds of thousands of dollars, millions of dollars, providing robust infrastructure, globally balanced, co-located data centers, data redundancy with master replica databases, all of this clever stuff that our server-side infrastructure friends put in place for us. And that's great. That's obviously a really important part of our companies and our businesses' infrastructure. To be able to provide the core services that keep your application up and running is important. But it's not the end of the story. There's a whole other class of outage, another type of downtime that we need to consider. And it's one that actually has just as much impact on the end user's experience. It has just as much impact on metrics, core metrics for your site, things like page views, maybe ad impressions, and revenue. But for some reason, this topic gets sort of lost. It doesn't have the focus at an infrastructure, at a business level for some reason. And that's something that really bugs me. And I think maybe it bugs me more than many because every day I go to this place, which is Brighton Station, south coast of England, where I live. And I get on one of these things, which are trains, for an hour in the morning, hour in the evening every day, backwards and forwards to go to London. It's great fun. And because it's such great fun, I need something to do. And I generally get out my mobile phone into settings and switch on Wi-Fi tethering. And off I'm ready to browse the web. And the next thing that happens is stuff like this, like tunnels. This is a tunnel, particularly elaborate tunnel that we have in between Brighton and London. But all sorts of things happen. Tunnels happen, remote countrysides happen, slow networks happen, unreliable, congested networks, sometimes no networks. And then the next thing that happens to me is something like this. So what's happened here? It's something that's become pretty common over the last few years. It's a website. You may be able to tell that it's a website, but there's no words on it, which is really annoying, because typically that's why I went to the website, to read those words. That's even more annoying, I think, if you understand that the words have downloaded, the words, it's somewhere between my phone and the computer, they're there, but the web browser's just chosen not to show them yet, because the font hasn't downloaded. So I'm stuck. And that's not a dig at fonts.com, that could be whatever service is providing your fonts, whether that's Google Fonts or Font Deck, or even if you're hosting them yourself. And it's not a service that's down here, it's not a bug, it's just how the site has behaved given this certain situation in a certain browser. But it's kind of an outage, right? There's no difference for me. I can't see the site, I don't know. It doesn't matter whether the server's down or whether the font hasn't downloaded yet. It's useless. I can't do anything with it. Because the network is basically unreliable, right? Networks go down, they get congested, they get slow, they disappear altogether quite often, particularly on a train. And I'm framing this in terms of trains and tunnels, but this isn't about trains and tunnels. There's any number of scenarios where the network can start to become a problem. Your code might get routed through a mobile operator's proxy, tries to compress the JavaScript maybe, ends up manuing it, introducing maybe a syntax error that means it just can't be executed on the browser. It doesn't happen so much these days, but it did 4 or 5 years ago. Maybe there's a corporate firewall sitting in between the internet and yourselves. Maybe that decides that JavaScript is dangerous and it wants to scan it and then strip it out. Maybe it decides to strip out clause headers. Who knows? We don't have much control on the network parts of the infrastructure that we all rely on. So it's kind of inherently unreliable. And the protocols that we built on top of it embrace that, right? We understand that stuff won't get there, there'll be packet loss, and the protocols know how to retry. But there's something else that we've worked out to help us with this. And that's that the web is inherently resilient. Things go wrong all the time on the web, and it still works. You send a browser some HTML that it doesn't understand, syntax error or whatever, it still works. You just kind of, ignore that, fumble through, so that I can show the web page. A CSS property is never heard of, doesn't matter, just ignores it, moves on. If an icon or a background image gets lost, it's not a problem, just be a little space there. You still get an experience. It's resilient by design, the web. And resilience is what's required when things have gone wrong. So what happens to a big, large, complex system when one part of it fails? Does the entire thing break and crumble at our feet kind of catastrophically, or can we still make progress? Can we still read some content? Can we still use the application? Can we still achieve the things that we came to the site to do? And the answer to this should be kind of obvious in my view. We've come up with a way of dealing with this already as web developers. We're used to working in this world where things kind of go wrong and it's okay. We've conceived a technique and a methodology that embraces that possibility, a technique for ensuring resilience in the things that we're building. So progressive enhancement is mostly considered in terms of technology support, so what happens to users who don't have JavaScript. But it's just as important, if not more important, really, to consider it in terms of technology failure. The reason we make websites work without JavaScript isn't for people that have switched off JavaScript in their browser. We understand that, right? That's a tiny proportion of web users. The reason we do it is to make our sites resilient. Resilient to failure because someone's gone into a tunnel, or an overzealous firewall has been stripping our important parts of our application out. The web is inherently unreliable. The network's inherently unreliable. We need to build that resilience through the way that we work with it. And for me, really, this is the use case, or the case, for progressive enhancement. If the company can make a case for this, spending thousands, millions on infrastructure to guarantee 4 nines, 5 nines of availability, scaling services to handle thousands and millions of queries a second. If they can make a case for this, then they can surely make the case for ensuring that their websites are not down for people who've had a bit of bad luck with the network. Because there's no difference for that user. There's no difference whether the site's down because the servers have disappeared, blown up, or if they can't see it because they've gone into a tunnel. That person's still a lost user. It's a lost page view, it's lost revenue. So, how can progressive enhancement help us with this problem? This is a strategy that I helped come up with at The Guardian, actually, and it works really well for the majority of content-based sites, news sites, e-commerce sites, certainly. And the way that it works is it defines 3 stages of priority. So the first is the content. This is the reason that people come to your site in the first place, presumably. In the case of The Guardian, it's the news. People come to read the news. It's the thing that we want to be top priority. We want to prioritise it over everything else that gets stuffed into web pages, which is a lot of stuff. Secondly is the progressive enhancement of that content. So this might be some JavaScript that adds some swipe interactions, maybe we want to add some touch improvements. Things like the Guardian fonts as well are downloaded as part of this enhancement stage. And finally is what I call the leftovers. So this is stuff that the user doesn't really care about. This is things like our analytics tools, third-party tracking, in the case of many sites that's advertising, things of that nature. The user's not too fussed about those. They can get probably even better experience without the tracking and advertising. So this is kind of a very high-level anatomy of page load. Is content, enhancements, and leftovers. So what does that actually look like when it comes to loading a page in a browser? So this is a waterfall chart, kind of you may be familiar with. If you're not familiar, it's pretty straightforward. It's basically showing every object, every asset that the browser loads as part of showing the page. It starts at the top left, going down the screen, time sort of going from left to right. And you can actually really clearly see these three distinct pages of the load, three distinct phases of the page load. So at the very top left there, the blue bar is HTML, and the green bar just alongside it is the CSS. And that's the content. That's it. Those are the only two things required for the browser to start showing the news to the people that have come to read the news. If everything else after that loads slowly or never, doesn't matter. They can still read the news. They've probably already started. They don't get the JavaScript enhanced experience, but maybe that's okay. In the middle, assuming they get that far, we load some of the JavaScript that does this extra enhancement, things like the fonts, other bits of conditionally load content, things like live sports scores, maybe top 10 articles, top 10 videos in this minute, and things like that. If the user gets them, that's great. They'll be happy, and maybe they find something they want to click on for their second page, and we get even more page views. Great. The bottom here in the final third is the leftovers. So if you look, probably can't see the URLs, but there's things like call to Omniture, which is Adobe's analytics package, some other tracking, empty.gif, that's nice. Definitely a leftover in my view. So by prioritising the HTML and CSS, we're attempting to get content on the screen as quickly as possible. The speed that we get things to show up is really important. In fact, certainly for a news site like The Guardian or BBC, it's the primary performance metric. It's probably more important than the download size of the page, like the total byte size. People get very worked up about download size, and wow, there was 3 megabytes of images on that page. And that may be important in lots of situations. It may be important for people's data connections on mobile and the cost of that, for example. But in terms of the performance metric that we want to prioritize the most, it is the speed of showing things on the screen. And if you can tie the speed that you show things on the screen down to a really core business metric like page views, then it's really easy to make that case. There's a lot of studies, which I'm sure you've seen, that say if you show pages quicker, people will visit more of them. The most fun way to sort of test this theory is to introduce a delay to showing your site. Maybe just introduce a delay, insert the initial HTML, 200 milliseconds. Just see if page views drop off on your site. It's quite a compelling case if you can see the data in front of people's faces. So what we're trying to do is optimize this time to screen in the way that we put our websites together. And to do that, we need to understand a little bit about how certain aspects of this web infrastructure that we're building with works. 2 areas in particular that I want to have a look at, which is the network. How does the browser interact with the network? And then also, what does the browser do once it's got some code, the HTML parser. So first of all, the network. What happens here? Well, when a browser wants to make a request for a web page, it starts typically with a DNS lookup. So it needs to find out the IP address of the machine that it needs to connect to. Now that DNS might be cached either by the browser or the operating system level somewhere. If it's not, then we have to go out to a DNS server. And hopefully we get the result of that lookup quickly, one round trip, hopefully. If the network's slow, or if there's some packet loss, then we may need to retry. There might be some congestion. And hopefully, once we do hit the server responds in a timely fashion. We can't always guarantee that. Once we have an IP, we can set up a TCP connection to the host. And again, hopefully this is one round trip on the network. If it's not, if there's a problem here, the browser needs to retry. Timeouts for this vary, I think, across operating systems. A while back, there was a version of Windows that had 3-second timeout on establishing a TCP connection, which is a really long time. Given we're trying to, we'd love to load a page in under a second. If we have a retry on TCP connection of 3 seconds, then it's game over. Once we have that connection, the browser finally can actually make an HTTP request for some content. We've probably already done at least 2, possibly 3, 4 round trips over the network by this point. If there's an SSL, if this is an SSL request, TLS, I should say, which I think increasingly is, of course, for a very good reason, we're going to have more round trips depending on the certificate and the number of hops in the chain to authenticate that. And finally, we should hit the server with our HTTP request, which is great. And there's a few things that might happen at this point. And one of the things that might happen, and is really common, is that we get an HTTP redirect and we go right back to the beginning. I feel like I'm going to cry just looking and just thinking about this. Like, this is one of the single biggest performance anti-patterns. Like, I hate them, and yet they are everywhere. There's like a whole sub-industry of URL shorteners that are just introducing redirect after redirect into people's web experiences. On mobile, it's just a disaster. And no company isn't doing this in some regard. People shorten their URLs, and then they go to Twitter. Twitter shortens it again, and then someone pastes that somewhere else, and no one's in control of this kind of chain of mess. It's really frustrating. So, given we've just gone back to the beginning, we now need to do another DNS lookup. The host name is different. We need to connect to that machine. We need to issue the HTTP request again. Assuming we don't get another redirect or anything, we now hit the server, which is great, because at this point we do start to have a little bit of control. This is our software running on the server. We can optimize it in such a way that it responds really fast. We can cache the right things. We could do things like flush the head of the document really, really quickly, so that the browser gets references to the assets in the head quickly. And eventually, send this HTTP response back to the browser. So we've just been through one HTTP request. It's complex, and it explains why reducing HTTP requests in general is a good idea. It explains why it's a good idea to reduce the number of CSS files you have being loaded, or reduce the number of JavaScript files you have being loaded. Wrap them all up into as few downloads as you can. Because the less time you have to go through all of these steps for each asset you want to download, the better off you are. Network requests are expensive, and we understand that, we know that from years of performance research and best practice. I guess it's peripherally worth mentioning HTTP 2 does help with some of these problems in that it does smart things around pipelining assets concurrently down the connection and things like that. So there is stuff happening at a kind of web infrastructure level that will improve this, which is great. Meanwhile, this is typically what we're working with. So first step, remove redirects. If you come away with one thing, let it be known that redirects are evil. As I say, they're everywhere. I mean, if you have any influence over this on your sites, places you work, try and do what you can to get rid of these long chains of redirects. I mean, redirects, they are required, right? Because if we want URLs to exist forever on the web, which is a nice, lofty goal that we should strive for, yes, we need to sometimes move content around and redirect users appropriately. But these long chains of redirect are just kind of, there are sort of chart looking back at the legacy technologies of any given company. And it shouldn't be too difficult to maybe tidy those up. Yeah, some other things that you can do to try and reduce the time to first byte, like the time in which the browser can start doing something with the response. But honestly, removing redirects is probably the one that you want to be looking into. So the next piece of the puzzle here is the browser. And as front-end developers, I guess this is the interesting bit for us, certainly for me. What does the browser do once it starts to get back some HTML? What processes occur for it to take that HTML, do the stuff that it does to it, and turn it into something that can be shown on the screen? Because that's the bit that we want to happen fast, right? And the first key thing to understand in this is that the browser's parsing and rendering loop is basically single-threaded. So that means, well, the essence of that means that it can only do one thing at a time. When it's parsing HTML, it can't be parsing CSS as well, it can't be executing JavaScript. And very broadly speaking, the browser's trying to get two things done at this point. The first is to construct the DOM tree, so the hierarchical representation of the HTML that we're used to working with when we work with HTML programmatically. So it's a tokenizer, works over the raw streams, it comes in, breaks these strings of HTML down, builds them into this DOM, so that the browser can start to understand the structure of the HTML. And alongside that, it needs to construct a render tree. And it does this from the DOM, and then from any style sheets that range through the middle page. And the render tree is a in-memory representation of where stuff will be laid out on the page. It's not showing it to you yet, it's just figuring out the broad kind of layout structures of where it's going to place pieces when it actually tries to paint to the screen. And once it's done these two steps for a chunk of HTML, it can then say to the browser, yeah, I've got a render tree here, like try and paint something. And the browser can go ahead and sort out the layout, calculate that, and paint something to the screen. So these are the two steps. This is a little visual representation of that process. You can see this HTML streaming in into the parser, constructing the DOM tree, the render tree, and finally getting to layout and paint. And there's various things that get in the way of this process, things that could block it on its critical path to the final step. And the most well-known one of these, which we've been talking about for years, but performance best practice for a long time, is the existence of a remote JavaScript file. If there's a script element in the HTML, the parser has to stop, has to go to the network, has to make that HTTP request. We know how problematic that might be, depending on the robustness of your network at this point. It has to download and execute that script. Nothing else can happen while it's doing that. So this is the classic blocking script scenario, and you almost certainly know some ways of working around this. We'll look at some in a minute as well. This is another problem, less familiar probably. Here we have a remote style sheet referenced, followed by a script node. So even an inline script node is shown here. If that style sheet hasn't been downloaded, the parser has to wait, because it doesn't know if the script is going to A, do something synchronous. Well, it should execute synchronously anyway, because it's an inline script there. And it doesn't know if it's going to reference the style sheet in any way. So it stops, downloads the style sheet, and then it can continue. So, how do we solve the blocking script problem? Well, for many years, people have been moving their scripts to the bottom of the page, like this, typically just before the closing body tag. And this is the reason why they do that, so it's not blocking the HTML parser from doing its job further up the page. Hopefully the browser renders quicker. And this approach still works really well. It removes that blocking script, it kind of defers its need to be executed much later in the page, which is great. This is another common pattern, which is to write the script tag into the page with a bit of inline JavaScript. So this forces the browser to download and execute the JavaScript file asynchronously. And you see this pattern a lot, but it has become a little bit of a anti-pattern now in newer browsers. And that's because it's hidden from browsers' preloaders. So modern browsers, we're talking, well, everything back to IE8, so a good few years of this now. They have a secondary HTML parser, it's sometimes called the preloader or pre-scanner or speculative pre-something. People call it all sorts of different things. Probably depends which browser engineer you ask. And what this does, it goes through the HTML looking for URLs of assets it thinks it might need in the future, and then speculatively downloading them even before the main HTML parser has got to them. So this is great because it means these critical resources start downloading quicker, and the main HTML parser ends up waiting much less time when it finally gets to needing them. You know, in the best case, they've finished downloading and they're in the cache, and there's no reason for the HTML parser to be held up waiting for the network. But the code here won't be found by the preloader because it's not just a standard script element. The preloader won't run that JavaScript to find out what it means. It'll just go like, this is not a link to some JavaScript, it's not a link to some CSS, so I'll ignore it. So that brings us to the third solution, and we're back at a good old-fashioned script element. Except this time we have a new attribute added, the async attribute, which was added in HTML5, so it's been around for a little while. And it basically tells the browser, download this script, but don't worry about executing it synchronously. It's saying, don't stop parsing HTML just because there's a script tag here. I promise that the code in this JavaScript doesn't need to do anything synchronous, it's not going to do anything mad like document.write. Go and download it, keep moving with the HTML parser, and just come back and execute this whenever you want. It doesn't matter. So yeah, it's essentially a promise to the browser that this script doesn't need to be executed synchronously. So with one of those approaches, you can make sure that the HTML parser is not blocked by any remote scripts, and it can move on to constructing the DOM tree for the HTML that it's downloaded so far. Until, of course, it gets blocked by something else. Something blocks construction of the render tree. What could it be? I hear you ask. Well, what could it be? Well, it is in fact style sheets, which I guess if you think about it is kind of obvious. The browser can't create a representation of the page layout if it doesn't have all the CSS. It can't show you the page until it knows where to put things. So CSS downloads are also blocking in this process. And that's often forgotten. We're used to talking about blocking scripts. We've talked about that as best practice for performance for many years. But the CSS is not really so different. And CSS is blocking to avoid, if you were around on the web, I don't know how long ago, probably again 10 years ago, the old, what do we used to call it, flash of unstyled content, where the browser would show you, it would render the HTML, like just standard HTML without any styles, and then as the CSS downloaded, it would kind of kick things into place, move around, and then you'd have a website. This was a bit of a janky experience, and it was decided that it would be best to make sure that there's enough CSS to progressively paint the page in a sensible way so that you don't have these multiple layouts, these kind of multiple relayouts. So we like that CSS is blocking in a sense, but it's unfortunate for render times because it means that most sites then require another HTTP request on their critical path of being able to show some content. And they're not really a bunch of clever solutions here, because the reality is you need the CSS to create the render tree. It's not like you have some asynchronous JavaScript and you can say, well, worry about that later. We do need the CSS. It has to be provided synchronously to the parser. So what some sites have started doing is putting CSS into the head of the document. So this way, into the HTML, so this way the browser gets hold of the styles up front when it needs them. But it doesn't have to make a separate request to the network and all the issues we know about speed and reliability that come along with that. Now, clearly we don't want to be putting all of the CSS for our site into the head of every HTML document we're serving. We'd end up doubling the size, well, more. huge grade of HTML files we have, we lose the benefits of caching CSS across multiple page views and all sorts of problems. So what we want in the head is just a portion of the CSS required to render the core styles, so typefaces, obviously the kind of main layout stuff, yeah, probably all your typography and layout, plus anything that's deemed critical for rendering sort of above the fold content. Now, of course, what is above the fold, it doesn't mean anything. It's likely to be different for every user depending on what device they're using, how big their font size is. So this is a little bit tricky. In my experience, you have to be prepared for a bit of experimentation and iteration on this to try and find like a nice sized chunk of CSS that you can put in the head and get your site looking really usable straight away. Really, it shouldn't be more than 12, 13K at the most. And this, again, this is fine. This is fine if you're in a position where you can experiment and iterate. If you're able to get feedback from users on, where some critical CSS is missing, layouts are jumping around a little bit. If you can get that feedback, iterate, change the CSS you've got in your head and deploy every day to try and improve this, that's great. It's a nice approach. If you're working with clients, maybe you're doing a handoff of a site, that's much more difficult because you can't, it's very difficult to get this right. You will never get it right. You'll always be kind of just doing the best that you can with it. But it is powerful because it allows you to remove one more HTTP request from the critical path of showing your content to users. There's a few tools that try and help you define what the critical CSS is, like they render the page in the browser and then go, well, what styles have been used within this box? But again, what box, what device? It's very difficult to really guarantee anything with these. So, to recap, the primary things that you want to avoid: remote scripts in the head that need to run synchronously, and style sheet downloads. Style sheet downloads for relevant media. So relevant media, what do I mean by that? I mean things that are going to be relevant to any media queries that are in the page. So if a style sheet has, let's say, a mid-width of 500-600 pixels on it, then an iPhone will download that style sheet even though it's likely to never use it, but it won't block the parser on that. It's smart enough to say, I'm not, like, my device isn't that wide, I don't need this to render, and it will deprioritize it. And this stuff, once you sort of understand what the browser's doing and how it goes from getting HTML to showing stuff on the page, a lot of these kind of performance best practices and ideas become kind of obvious. It's like, oh yeah, if we did that, we'd remove this whole class of problem where the browser's slow at this point. You can start to fix the things. And, like, really, this isn't any big, new, exciting idea. This is similar to how you might architect for failure in any large system on the server side or whatever. By swim laning services, this idea of fault isolation, not having one piece of your system that everything else depends on fundamentally. Just try and take those things so that they're not so tightly coupled. An e-commerce site like Amazon, for example, Amazon.com doesn't need to be down because their payment gateway is having problems. You can still browse the product pages, you can still sign into your account, you can probably do all sorts of things. You just can't pay for the things at the moment. And that's probably fine for now. That's better than Amazon.com being down. So they decouple their infrastructure in this way. The quote here, uptime is not binary, that's a quote from, I think his name is Mike Britton, who was a operations or infrastructure manager at Etsy, who were very kind of clued into this idea of making sure you deliver some experience to users, even if, like, behind the scenes things aren't going well. So, coming back to this is my big bugbear, and we haven't really talked about why this happens in that process of HTML turning into things on the screen. This is another example from a few days ago. This problem is particularly bad on mobile Safari, and we'll see why that is in a moment. I was trying to read an article on the next web and I couldn't. Again, the page has been painted. You can see where the text should be. So we've done a really good job, potentially. I don't know if next web really do, but they have managed to show me something on the screen. That's great, but just no text. So why does this happen? So with the font stuff, you don't delay the render of the page. You just introduce a new dependency that blocks the text render. But it's basically the same result, right? Because there is no text. So by adding all these font downloads, we're increasing the possibility of content not being displayed because we don't know if these critical resources are going to get spoiled by a dodgy network or lost altogether. And this is what's happening when text is missing on the web. There's been an issue with the network somewhere in here. After the render, we've managed to paint to the page, but we haven't got the fonts yet. And different browsers do slightly different things here. I'll start with Internet Explorer, which is kind of the most conservative and the most resilient. It always shows you a fallback font while it's downloading your custom web fonts. And then once it has those available, it will repaint that text. Sometimes you get a little noticeable flash of the font changing. Although there's smart things you can do to make sure that the font sizes match and the spacing between things match. Safari, mobile Safari, both block showing text until they've got the fonts. It's really unfortunate that that's the case on mobile Safari because that's the one that people are most likely to be using with high latency networks on mobile. Chrome, Blink had this issue until, I don't know, recently, 36, when was that? And now what they've moved to is a model where they don't show any fonts, but if the fonts are slow, if they're waiting, I think it's a 3-second timeout, then they go, okay, we can't keep waiting for these, let's show the content in a fallback font. It's quite a nice compromise. So what can we do about this? There's a few things we can do. One that I like is Web Font Loader. This is an open source JavaScript library developed by Typekit and Google. And the goal of it is to provide a bit more control over the loading and rendering of web fonts. So it helps remove fonts from that critical path, and it can help you make the way that fonts load, these different scenarios that I outline here, in a more consistent way. You get a little bit more control. So a common way of implementing web fonts is to have a set of CSS files. Something like this contains your app font-based rules. And this might be some CSS that's hosted by a third party, fonts.com or Fontdeco or whatever, or maybe it's on your site. And yeah, you link to that style sheet using a plain old link element like this one. And that gets your fonts into the page, but it has this blocking rendering problem in mobile Safari. So with Web Font Loader, what can we do to fix that? Firstly, you won't need the CSS link element anymore. What you will need is a little bit of configuration in JavaScript. That holds the names of the fonts that you're going to load and the URL of the CSS file where the app font-based rules are. Once that's set up, you can load the JavaScript library that implements this, and that gets the browser to start downloading the fonts without blocking the text rendering. And once it's doing that, once it's done that, it puts us in a position to decide how and when we want to render the fonts on the screen. The way that it does that is to give us access to various events that occur as the fonts are loading. And one way it exposes those is with class values on the body element. So at various points in the process, it adds these class names and then we can target them with CSS. So for example, while the Clarendon font is loading, we have this value Clarendon loading applied to the body. Once it's finished, it's replaced with the class value Clarendon loaded. Quite straightforward and obvious. And really easy to work with because it means we can now do something like this in the style sheet. Excuse me. So the first CSS rule here would ensure that the H1 was rendered in Georgia by default while the font is loading. Like if anything goes wrong now, we're still going to get the font shown in Georgia, which is great. It's the resilience that we're looking for. Once the appropriate font has loaded, then the Clarendon loaded class value is added to the body, and that second CSS rule kicks in, and we show the newly downloaded web font. And that's kind of the most basic way of using web font loader, but it's powerful because it takes fonts out of that critical path. It ensures you don't have this single point of failure for showing your content to users, particularly when that might be a third party, and you don't necessarily have the kind of SLA that you might want from them. So there's a new-ish, it is implemented in Chrome and Opera, I think. The CSS font loading module gives you alternative native ways of doing a similar thing. So you can see document.fonts.load, you give it a font name, it returns you a promise, and you can wait for that, and then once it's resolved, you could add the class name to the body yourself and take the same approach. There are polyfills for this, because the web font loader API is slightly different, clearly. But the reason I like it and recommended it, it has a lot of history. It's been around for 5 years. It feels to me like it's well back and tested. So, to start summing up, I want to go back to another waterfall chart. And this one's using a tool called Web Page Test, a great tool for ad hoc testing of web performance. And here, I have not highlighted the right bit. The reason this happened is because I changed my slides from different resolution this morning, and I didn't move the red circle. The red circle should be around the top left blue bar, and what it should be showing is that there's now only one HTTP request required to show content on this site. And this site is The Guardian. This screenshot was taken a while back. But one HTTP request to show the news, because the CSS is in the head and there are no blocking scripts. That's pretty resilient. When I load that site on my mobile phone on the train, I'm kind of confident that I'm going to get something back that's useful to me. It's also how The Guardian can get performance results like this from Web Page Test. So this is showing the median start render time for an uncached page. Median over 9 test runs. It's under 1 second. In fact, it's about 3/4 of a second. And this test was done on an iPhone 4 on a 3G network. So it's fast and it's resilient. And that means I end up with this nice train experience. But we know this is not about trains and tunnels. It's about making pages that don't fail when one thing goes wrong. If that thing is the network, we're in trouble, because we know the network is an uncertainty. Things go wrong with it all the time. We accept that. We know how to work with that. We work with it in the way that we build our sites, the way we architect the front-end code with some of these approaches, so that our users have the best chance of consuming the content and using our application. We need to build resilience into the way that we construct and put these web pages together. Thank you.
Thanks very much, Andy, for an in-depth look at how browsers actually show the page.
Not too dry.
Who knew it was that complicated? Are there any questions for Andy about all of this stuff? Did you see the Tab Atkins proposal for a new thing in the font family, display font colon optional, which says if this font is in the cache, use it. If it isn't, then just go out and fallback, but asynchronously download it for next time.
For the next page, yeah.
It's really cool.
Yeah, at The Guardian, we played around with, and actually I think there's still an implementation in production of doing our own caching with base 64 encoded fonts and putting them in local storage, checking if they were there, and if they are or not, make a decision about what to do. I wouldn't recommend necessarily that, because the complexity might be too much for the value. HTTP caches are okay.
Yeah, it's a bit Rube Goldstein to go back to what Stephen was saying earlier. Well, ladies and gentlemen, Andy Hume. Thanks, Andy.